Right. Hey, everyone. My name is Lei Yang, and I'm the CTO of MegaETH Labs. Today, I will share some performance-related works that we've been doing here at MegaETH, and you will take home a deeper understanding on the performance of the Ethereum execution layer, and you'll also learn our vision of future high-performance blockchains. At MegaETH, we're accelerating Ethereum at layer 2. So most of our work focuses on improving the execution client. However, it is impossible to design a truly high-performance system without first understanding the state of the art. Unfortunately, very few people besides the core devs understand the existing Ethereum execution layer, especially its performance and limitations. And we cannot find any good performance data or analysis. So we decided to take a rigorous approach called measure then build from the very beginning. From following this approach, we first perform thorough performance measurements to learn what real problems are in the existing execution layer, and then we design new techniques to solve these problems. There are two parts in this talk. In part one, I will share some interesting lessons that we learned from profiling the Wrath execution client. It's a new client developed by Paradigm and written in Rust. I'll explain why your Ethereum execution client today is slow and how they perform under different environments. And then in part two, I'll share our vision on scaling Ethereum at layer 2 and how much performance we can ultimately squeeze out of it. Due to the time limit, I'll focus on part 1. So let's dive into it. Before we start talking about the numbers, I'll quickly explain what is the execution layer. On a high level, a blockchain hosts a bunch of decentralized apps or dApps, and users want to interact with these dApps. They do this by submitting transactions to the blockchain. First, the consensus layer decides which transaction comes at what time, so it establishes an ordering of all the transactions. And then the execution layer executes these transactions in that ordering to update the blockchain state. The program that powers the execution layer is called the execution client, and it has two main tasks. One, execution, and second, merkleization. Execution means processing the transactions and updating the blockchain state, as I just mentioned. And merkleization means updating the state Merkle trie after the state changes. And the state Merkle trie allows users to easily verify the state without executing the transactions by themselves. So it's also pretty important. Wrath works in batches of blocks. For each batch, it first executes the transactions, gets the new state, and runs merkleization, and finally saves everything to the disk. There are two modes in Wrath that differ in how large batches they use. One is historical sync, which people use when syncing from the Genesis block for the first time. In this mode, Wrath uses large batches and only updates the state trie after processing a large number of blocks. The other is live sync, which people use when the client is already synced up and wants to keep track of the chain tip. In this mode, Wrath updates the state after every block, and also the state Merkle trie after every block, so the batch size is 1. Our test server is very beefy. It has 500 gigabytes of memory and a very fast SSD. The CPU core count here doesn't matter because the workloads are single-threaded, so it cannot use that many number of cores anyway. To simulate machines with different memory sizes, we also use a tool in Linux called cgroup to control the amount of memory available to Wrath. And we run many experiments in different configurations, trying both historical and live sync in Wrath, and also different memory limitations. And then we can study how Wrath performs under these different configurations. Recall that Wrath has two tasks, execution and merkleization. Here, first, we only focus on execution. And in the first experiment, we run historical sync with all 512 gigabytes of memory available. And we use a batch size of 500,000 blocks. In other words, we store new states to the disk very infrequently, and we also update the Merkle tries very infrequently. The graph shows the execution throughput, or the number of transactions it can process per second, and we show how it changes with the block height. Each blue dot in this plot is the throughput of a particular block, and the red curve is the moving average. Overall, it took us about 24 hours to sync 18 million blocks to the tip. And if we zoom into the most recent 1 million blocks, in other words, the most recent, the current workload, we can see that REST can process about 14,000 transactions per second. So this is actually pretty impressive. And if we measure the throughput in terms of the amount of gas it can process per second, we see that REST can achieve 1 to 2 billion gas per second for the most recent 1 million blocks. So the key takeaway here is that modern EVM implementations like REST is actually doing pretty well already. At least we'll give it a gigantic amount of memory, enough to store the entire database in the memory. So how large is the database? This screenshot shows the size of database tables in a fully synced up REST archive node. So at the bottom, you can see that the total size of the database is about 2.3 terabytes. So this seems pretty large, but fortunately for execution, we only need the so-called plain state tables, and that's about 100 gigabytes. By the way, if you also want to fit the entire state Merkle trie in the memory to help with Merkleization, there's another 126 gigabytes. This figure breaks down the amount of time cost by different steps in execution. The red part, which is the majority, is basically running the transactions and the smart contracts they call. And it takes 2/3 of the time. So this red part, or actually running the transactions, is indeed the main bottleneck of execution. And I'm pretty sure that we can further optimize the other parts, so the percentage of the running the transactions will only get higher. To understand why running the transactions takes so much time, we instrumented RAM interpreter, or REVM interpreter, used in REST to collect more metrics on each EVM opcode. And we get this table. It contains a ton of interesting information, probably too much, so I'll quickly walk you through it. In the table, each row is an opcode, and each column is a different metric. So for each opcode, we have the number of times it's invoked, we have the amount of time spent on it in seconds, and we have the percentage of total time spent on a particular opcode. Here we order the opcodes from the most to the least time consuming. And we can compute the amount of time spent by the top K opcodes. We can also compute the average time per invocation. And finally, we can group the opcodes into a few categories based on what they do. Based on this table, we can plot the 30 most time-consuming opcodes. Here, the x-axis is the opcode, and each blue bar shows the percentage of time spent on an opcode. And the red curve shows the cumulative percentage of time spent by the first X opcodes, starting from the leftist. And here are some key takeaways. First, 90% of the execution time is spent on the top 30 opcodes. And the top 5 opcodes are static call, keycac 256, sload, call, and push 1. We can see that when the state database fits in the memory, sload, which is about loading the state from the database, takes only 8.8% of the execution time. So state access from the database or database read is definitely not a bottleneck here. And execution is entirely compute bound. We can also group the opcodes into a few categories based on what they do, and it gives us some other insights. First, host and system opcodes on the left-hand side takes more than 50% of the time. Host opcodes is to interact with the EVM environment, such as reading and writing the storage. And the system opcodes are basically keycat 256 plus a few other functions. These opcodes are relatively complex, and they are already implemented in the native programming language of their execution client. So in other words, they are precompiled for the actual servers, the bare metal servers they run on, and has relatively little overhead. Second, stack operations take another 29% of the time, and the remaining 20% of time is spread across arithmetic operations, bitwise operations, control operations, and etc. So there has been proposals on compiling smart contracts using or either ahead of time or just in time or JIT compilers, but since system and host opcodes are already written in the native language and already compiled, a JIT compiler or an ahead of time compiler can only accelerate the opcodes on the right hand side of the chart. So at most, it can achieve a 2x speedup. All right, now we have a pretty good understanding of the execution performance when there is a large amount of memory to fit the entire database. We saw that REST is actually pretty fast in that case, but what if this is not the case? What if we don't have enough memory to actually store all the relevant information that the client needs for execution and localization? The folklore says the performance will suffer a lot, but is it really true? Let's find out. To understand the impact of limited memory, we rerun the experiments under smaller memory sizes from 8 gigabytes to 512 from 8 gigabytes to 512 gigabytes. In addition, we reduced the batch size from 500,000 blocks to 1,000 blocks, so the experiments do not run out of memory. And the result we get is a surprise, and it's a surprise in a good way. All right, this plot shows the time to execute the most recent 1 million blocks as we change the memory size available to the REST execution client. The blue curve is the total amount of time spent when there is a various amount of memory available. And we can see that as we go from 512 gigabytes to 8 gigabytes, there's only a slowdown of less than 2x. And that means that with just 8 gigabytes of memory, we can still achieve 7,000 to 8,000 transactions per second, which is still pretty impressive. And the other three curves on this plot give us some insights into why. From top to bottom, the orange curve is the time spent on actually executing the transactions. The green curve is the amount of time spent on loading data from the disk during execution. So it's a portion of the orange curve. And at the bottom, the flat red curve is the cost of writing the new states back to the database or to the disk. See that as we reduce the memory size, the total amount of time, or the blue curve, increases only because the green curve increases. In other words, as we reduce the memory size, we spend more time fetching data from the disk because, again, the entire database cannot fit in the main memory. So some data has to live on the disk, and when we use them, we have to go to the disk to fetch them. But the question still lingers. As we decrease the memory size by 64 times from 512 gigabytes to 8 gigabytes, why is there only a slowdown of less than 2x? It seems too good to be true, right? It turns out that this is because Ethereum transactions has very strong temporal locality. It means that the data that are used recently will very likely to be used again in the near future. And because of this nice property, you can use a technique called caching, which basically keeps the data that you just used in the main memory. So it will be easier and faster to access when you use it in the near future. This figure shows the two-level cache architecture of REST. When EVM needs to access some data, it first looks into REST on cache. And if it couldn't find the data there, REST looks up the underlying database, which has its own cache. based on our profiling, the miss ratio at these two layers are 21% and 31% respectively. In other words, only 6.45% of the requests actually hit the disk after missing both caches. And our data shows that the average miss penalty is about 80 microseconds. In other words, the time to access the disk to get the data that is not presented in the cache is about 80 microseconds. So this low miss ratio explains why we still have very good performance when the memory size is much smaller than the database size. Because again, very few requests actually go to the disk, even if we have very limited memory. All right, so far we have been studying the execution only. So let's now include merkleization. On the left is the throughput graph of the historical sync I just showed you earlier. And we saw that RETH can achieve 14,000 transactions per second for the most recent 1 million blocks. And this is what happens in live sync when the batch size is set to 1 and REST has to update the state trie after every block. The throughput drops dramatically to 1,000 transactions per second by almost 14x. And this is even the case when the entire database fits in the memory, both the plain state tables and the Merkle tries. And why that's the case? Our data shows two main reasons. One is the cost of merkleization, which incurs a 9.3 times slowdown. Again, this happens even when the entire state trie fits in the memory. Second, on top of that, writing the new states every block incurs another 1.5 times slowdown. But why is merkleization so expensive? Well, the reason is that updating the Merkle trie requires a lot of trie traversals, and each incurs a lot of database reads. And although the database fits in the memory, the overhead from the software of the database management library, or MDBX, is pretty high. And it's about 1.2 microseconds per read operation. And this overhead adds up when you do a lot of reads when you are updating the Merkle tries. So now what if Merkle trie does not fit in the memory? Well, it gets even worse. We rerun the live sync experiments under different memory limits, and the table summarizes the results. It's easy to see that the cost of merkleization far exceeds the other costs, including execution. And if we decrease the memory limit from 512 gigabytes to 8 gigabytes, merkleization is 6.9 times slower. So this results in a further 5.3 times slowdown of the overall throughput. And the throughput drops from about 1,000 to 200 transactions per second. Now let's do a quick recap of our journey before we conclude part 1. We started with a nice and juicy 14,000 transactions per second with historical sync. We added merkleization so that REST runs in live sync mode, and the throughput drops to 1,000 transactions per second. If we further reduce the memory amount from 512 gigabytes to 8 gigabytes, say, we end up with just 200 transactions per second. And finally, if full node operators only want to spend 10% of their CPU power or their machine's power on block verification, then we're looking at perhaps a miserable 20 transactions per second. So we're basically dropping down to the layer 1 Ethereum throughput. So you see where this is going, right? Fortunately, we can do better. And I'll start part 2. At MegaETH, we believe that layer 2 is the best place for performance innovation. Why? Because layer 2 enables what we call heterogeneous scaling. That is, there can be different types of nodes that vary significantly in their numbers and hardware requirements. For example, at layer 2, you only need a few sequencers, so you can afford to run them all on very beefy machines like we used for our experiments. And if you're doing ZK rollups, then the prover nodes can run on specialized hardware like ASIC or GPU to speed up ZK proof generation. Or if you're doing optimistic rollups and you design the challenger nodes to be stateless, then their hardware requirement can be extremely low. Finally, full nodes don't have to re-execute the transactions, so they can run on cheap commodity machines, and there can be hundreds of thousands of them. So note that here the basic idea of heterogeneous scaling was introduced long ago. For example, Vitalik's endgame post argues that if you want high performance, then inevitably you have to relatively centralize the block production. And it is fine, actually, as long as there's some anti-censorship protection and block validation remains decentralized. We said the sequencers can be very powerful machines. So let's just run them on Solana level servers. Each server has a dozen CPU cores, at least 256 gigabytes of memory, fast SSDs, and more than 1 gigabit per second network bandwidth. And we can also apply all the software optimizations that we know. For example, to improve execution performance, we can use parallel EVM to better utilize the multiple CPU cores and I/O parallelism. We can also compile EVM bytecodes to native code to boost single-threaded performance. And for Merkleization, we can parallelize the Merkle update process, which Rath doesn't do it for now. And we can also optimize the database to get rid of the overhead. We can even design more efficient data structures to replace Merkle-Patricia trees to store the state trie. So in the future, we can expect that a hyper-optimized sequencer software and hardware can achieve an order of magnitude higher throughput than historical sync in Rath today. In other words, that will be 100 to 200 thousand transactions per second on the current Ethereum workload. But actually, sequencers are not the main problem. The real question here is whether the full nodes can keep up with the beefy sequencers. So now this is your full node. It might be a used laptop sitting on your desk, and maybe it has 4 cores, 8 gigabytes of memory, and 100 megabit per second network connection, which is tiny compared to the sequencers. How can it keep up? First of all, layer 2 full nodes can rely on external proofs like ZK and optimistic proofs to check the correctness of state transitions. So they don't have to execute all the transactions like sequencers do. They can just download the state diffs from the sequencers. And another nice thing is that state diffs can be highly compressed, so it does not stress the precious network bandwidth. Second, after downloading the state diffs, the full node needs to apply them to its local database. Fortunately, these batched writes can be made very efficient. And the temporal locality I mentioned before also helps because we can use the same trick of caching to reduce disk I/O. Finally, the full node needs to update the state trie if it wants to serve light clients. The state trie will be too large to fit in the main memory of the full nodes, so this is actually likely to be the most challenging task. But we think it's actually doable by combining a number of smart optimizations. So here's our vision for high throughput future layer 2s. We call them mega rollups. By the way, I'm pretty sloppy in terms of the use of terminology here, so feel free to replace rollup with layer 2 or Ladinium, but basically any term that you see fit. Our vision here is that in the future, each mega rollup of optimistic or ZK will reach 100 to 200,000 transactions per second, and it can support a very large state, think terabytes, without degradation in performance. And there can be hundreds or thousands of them. The sequencers will somehow be decentralized to prevent censorship, but we don't want to reintroduce consensus or network bottleneck. Mega rollups must be built on very high bandwidth data availability layers like EigenDA. And maybe if Ethereum were to become a bottleneck in settlement, we also need a specialized high performance settlement layer. So that's all I have today. And I would like to encourage you to check our Twitter account for more information.